Hello, community. In context learning, we use it every day, but today we're going to try to understand what it is. And we're going to have a look at a quantum interpretation, and then we morph it into a wet biological cell, the learning of ICL. You remember, language model must extract signals from individual few-shot example, then somehow they aggregate this, they learn here a new rule, and then they apply this rule to our query. But now the main question is, how is this implemented in the forward pass of a modern transformer model? And we take the simplest task possible. This is just add an integer, add k. So, let's have a look. We have a brand new research here from UC Berkeley. In context learning, you remember, is different from fine-tuning. And in this video, I showed you here, if you are smart, you combine both of them. Because in context learning has a deeper learning operation pool than fine-tuning. If you want to learn more about this, this is the video for you. So let's start and have a look here at the attention head in a layer of a transformer. And you know this thing, we have talked about this quite intensively. Now, in the simplest case, our output vector here of the attention head is about a 128-dimensional vector representation, and it consists of a pattern of activation. Why of activation and not of tensor weights? Because, yes, of course, fine-tuning changes here the tensor weights in our layers. But if we only have in-context learning, if we have no access to the real models here, then we only have here activation that are calculated. And this pattern of activation is also an internal representation of the task parameter k for our simplest possible task. And just to give you a feeling, a Llama 3, 8 billion free trainable parameter has about 1024 attention heads. So now we look at how does 1024 attention head, each computing a 128-dimensional vector, come together to add one integer? I mean, it couldn't be simpler, no? Well, talking about simple, what do you think we use code? And I do a code morphism for you. Because you might say, hey, that's too boring. No, I can read the paper by UC Berkeley myself. Is there something more challenging for us here? And I say, yes, of course. You know what? We morph now the code of an ICL add k task. We use this now and we morph it into a quantum-like simulation where the information about k is now encoded in specific entangled states within a subsystem. So now we all become, for a very short moment, a quantum information theorist that we are now measuring and characterizes those k states and their dynamic now in a quantum-like simulation. Yes, we start slowly to jump over to quantum mechanics, AI, and quantum information. So at first we have to identify that we do have here the appearance of a coherent subsystem. And this theorist now finds that the quantum state representing here this particular parameter k is not diffused across the entire Hilbert space of our large language model. So this means the system itself decides to focus on a specific coherent subsystem of just 3 quantum registers. Those quantum registers in our cohomology is an attention head, of course. And this holds here and processes here this k-relevant information. Now, interestingly, we also have here a k-eigenbase. This is now a 6-dimensional subspace in our quantum dimension. So with each of those 3 registers, the possible states, if you want, the quantum states of k, they do not span here the full 128 dimension of the attention head, as I showed you, but less. Interestingly, UC Berkeley now found that doing now the add k calculation, they are only focused here on a 6-dimensional eigenbasis. And this eigenbasis, you're familiar with this, is now a 6-dimensional subspace in our quantum simulation. So this means the measurement outcome for k is simply determined by projecting onto this restricted basis. We have found the nucleus in our quantum calculation, the subspace that is really responsible for doing here the operation. and all the rest is doing something else. Let's talk about the phase coherence and a quantum frequency encoding mechanism. And yes, there is something similar. So let me start by trying to interpret this here. Those eigenstates within our six-dimensional eigenbasis are not random at all. They exhibit here a specific phase coherence if you want a superposition. You remember Schrödinger's cat, superposition of life and death? Now we have a different superposition. We have a periodical superposition within K. So it gives us here, interestingly here, the six-dimensional space, as I told you, is structured, but now it breaks down in a four-dimensional space and a two-dimensional space, and they encode different features. The four dimensions here of these spaces show here interference patterns, and those are, in the simplest case, trigonometric functions that align very simple with a mathematical operation k modulo 2, k modulo 5, and k modulo 10, encoding here the unit digit of k through specific quantum frequencies. And then, this is absolutely fascinating, we have two other dimensions, and they encode now the overall energy level, or if you want the amplitude of k, but in the tens digits, so for the longer wavelength periodics, especially periods from 25 and 50. This is absolutely fascinating. So the AI chosen now not to do a simple mathematical operation, but to go here into this particular subspace, then have here a particular task orientation of this subspace, and then we build here a specific quantum state in a superposition with this periodic eigenbasis. Interesting to learn that this is the mechanism for in-context learning. Now, let's have a look here at the state preparation phase. You remember the different quantum physics here in university. The moment you measure something, it collapses in a quantum mechanical state. The same is happening here. If we have here a measurement of yi observable of this particular token, the system effectively collapses here, the complete system, to a single state representing here exactly the difference. So this is exactly the result of this operation would be our K. This means we imprint here our K in the measurement of a quantum system that collapses to this particular state representation of K. We have even some more weird thing going on that UC Berkeley found, of course not in the quantum space, this is just between you and me. We have a decoherence mitigation or a quantum error correction happening in the system. I told you from our 128-dimensional space we only have 6 active. No? The rest of this, the other 122, call it noise if you want. No? But this noise comes in sometimes in our calculation, in our quantum calculation. So there is now a particular mechanism that tries to cancel out this noise from the rest of the complete space that would be available of the Hilbert space, but we simply don't need it. So if you want, we have a very basic rudimentary form of a quantum error correction or of a state stabilization here in the quantum mechanical image here. That is taking place here, and I think this is fascinating. Remember, our mathematical operation is just to add a simple integer. So what is here, if you want, if we have this code morphism, a quantum insight? The LLM's internal representation of K for the simplest in-context learning task, where we provide some examples here, resembles here really a quantum-like information encoding scheme. It uses here a highly compact, specialized subsystem, 6-dimensional, where K is represented not as a classical variable, in the classical sense and the Newtonian sense if you want, but as a structured quantum state. Within, and now this is fascinating, a low-dimensional, 6-dimensional, period-defined eigenbasis. Eigenstate, eigenbasis, eigenvectors, you know exactly what we are talking about. So this means that this ICL process itself is akin to a state preparation and a decoherence mitigation. If you found this interesting, let me go here a little bit further. So here at the top, you will see here the interpretation by UC Berkeley here for the non-quantum simulation. So what they found is here, this 128-dimensional output here of this single attention head, it's 3 as we know now, is simply too large and potentially redundant for encoding here this relative simple concept for add k task. And k should be between 1 and 30. And they found here, and this was great, please read the paper, that only a 6-dimensional subspace captures here close to 97% of the task relevance variance. So they found out, hey, we don't need the other 122 dimensions, no? If I bring this over now in the quantum simulation, it is a quantum register. My attention head is simply now a quantum register, and it might have all the 128 potential qubit dimension, the degrees of freedom, in the worst case. So performing computation, storing information, of course, all these dimensions for every single task would be really expensive and absolutely inefficient. And the system itself decides to collapse to a k eigenbasis, and this represents a highly compressed, resource-efficient encoding for this particular task. So to perform a particular task, to perform a learning, just on the activations, the system comes up with this solution. So the system has learned that for add k operation, it only needs to manipulate and measure states within this specific 6-dimensional slice of its total available Hilbert space. If you want, it's like finding a shortcut, yeah? Now, okay, Berkeley comes back and says, hey, the other 122 dimension of the head's output likely carry information relevant to other things, no? Contextual nuances, general linguistic processes, great. So, for this particular task of add k, this we can regard just as noise. Sorry. Now, the full 128 qubit dimension might be now, and you know this now, susceptible to various forms of environmental decoherence or entanglement with irrelevant parts of a larger quantum system. Interestingly, those k eigenbases acts now as a protected subspace where the k information can be maintained with a high fidelity. I found personally this absolutely fascinating. Yeah. UC Berkeley goes on and says the 6-dimensional space is not just any 6-dimensional, it is structured. The LLM decides here from its matrix operation, matrix multiplication, to define a structure for this particular task. And it further decomposes here into meaningful components related here to a unit, digit, and a magnitude of k using here periodic function. If you think about this, this is simply amazing to see. This is the way in context learning is happening in a llama, 3-8 billion model. You have a unit digit, you have magnitude of k's, and you have an encoding in a linear combination of periodic functions. If I morph this now to my understanding as a theoretical physicist, now, our k eigenbasis is not just a random projection. Its basis vectors here, if you want the feature directions here, have specific physical meaning. If we then move to real physical world systems, you will see that this will become extremely important. For now, in a mathematical operation to add just an integer to another integer, so the mathematical meaning is not that significant here, but it will when we encounter the real world. Yeah, so anyway, this corresponds here to eigenstates that are particularly sensitive to the periodic properties of k. So this specific structure allows now the system to interpret the state within this spaces in terms of the properties. For example, measuring a high amplitude along the period 2 eigenstate directly tells the system about the parity of k. And without such a structured eigenbasis, the quantum state might be simply uninterpretable mess. Isn't it beautiful what happens here on a mathematical side? UC Berkeley goes on and gives us the sentence that computation for extracting and applying k seems to happen largely within this six-dimensional subspace. And we say from a quantum morph system, yes, of course. Because guess what? This is exactly the K eigenbasis that defines here the set of the allowed quantum operation, or of the transformation that we need in our quantum computation, or in the simplest case here, to the add K task. So manipulating now the quantum state of K within this basis allows here for predictable and robust evaluation of the states and conditions. Yeah, if you go with apply the arbitrary operation across somewhere in this 128-dimensional world, yeah, just computational errors. This is not the way to do it. So the eigenbasis here in a quantum simulation provides here in itself a stable computational arena, a subspace, where this is the best place to do the mathematical operation. UC Berkeley gives us in the sentence, the LLMs learns to use this subspace and its periodic features. Great. Now if we look at here this morphed quantum physics idea, we say through the training, so interaction with vast quantum environments, the system has somehow discovered that these 6 specific degrees of freedom and their periodic interrelation are the most salient features for representing and manipulating the concept of K in the context of the mathematical operation of adding an integer. So the K eigenbasis represents the learned fundamental quantum variables for this task. And this is fascinating that an AI can do this. So again, short summary, this K eigenbasis that develops out of the system, out of the training, out of the in-context learning is absolutely needed, and it is beautiful, it's amazing, this feature. Why? Because it makes the representation of K compact. It isolates here the K signal from the other noise, the other 122 dimensions. It provides the necessary structure for interpretable encoding based on the periodic properties, and I'll show you those in a second. It defines a stable computational subspace for our quantum calculation, and it enables generalization. It enables learning to unseen data. Is this amazing or what? So let's have a look here. Beautiful study by UC Berkeley, published yesterday, May 8, 2025. Great authors here, understanding in-context learning of addition via an activation subspace mechanism. And they invested this here not on a quantum level, on the classical easy code level for a Llama 3 8B. So let's have a look here for the original publication that you also have here, the published version here. They say, okay, so if we have K, let's say K is from 1 to 30. For the specific attention head that I told you, we now collect here 30 different 128-dimensional activation vectors, our attention head vectors. And then we perform, in the simplest case, a PCA analysis, a principal component analysis, and PCA finds there are specific principal components in this 128-dimensional space along which those 30 attention head vectors vary the most. And the authors find that the top 6 principal components capture almost all the variance related to our parameter K. So if they then examine here the coordinates of each of HK along these 6 principal components, that is, they simply have an inner product, it reveals an activity profile. And this activity profile is interesting. Let's have a look at this, because you will see here in those, let's say, 6 components, they have here partially periodic patterns. Now you can see it. It's not really a periodic pattern. It's not really something clear. But if you look at this, maybe 6 is a little bit different, but the first 5 definitely, you can see periodic patterns. Yeah? So what do we do with this? Well, Fourier transform and everything, you're expert in this. mathematically, if we can find a linear transformation of the 6 principal component coordinate function that will fit, in the simplest case, trigonometric function, then by applying the transformation on the PCs, we can obtain our 6th direction whose coordinate function encode the periodicity. Look at these images. Isn't this beautiful? Modulo 2, modulo 5, modulo 10 cosine sinus, modulo 25, modulo 50, and you have here the target periodic function and the constructed coordinate function. They fit almost perfectly. So this is the way UC Berkeley did it, not on the quantum level, and they found 6 trigonometric functions at the periods 2, 5, 10, 10, 25, and 50. And now the authors says, hey, let's have an idea, yeah? And again, this 6-dimensional subspace, maybe we can subdivide it and find here further information. And they say the feature direction corresponding to the period 2, which they call the parity direction, encodes the parity of K. And the subspace spanned by the feature directions within the periods 2, 5, and 10, they call the unit subspace, and it codes the unit digit of K. And then they have another this is a 4-dimensional, another 2-dimension, the subspace spanned by the direction with periods 25 and 50, which we call the magnitude subspace, encodes the coarse magnitude, this means the 10 digits of K. So you see, we got now an interpretation, and let me show you a very interesting image here. If you have a mixed K ICL prompt, you see, from 15 to 17, yes, you have to add 2. From 55 to 64, you have to add 9, and you get it, yeah? And then they calculated here the inner product between the projected signal from each yi and each head vector hk projected onto the subspace and normalized, they have a unit norm and whatever. And they see now for each example here, the inner product peaks exactly for K as, if you want, the difference between given here, the xi and the yi, indicating here that the model really extracts the information from the corresponding examples. And as you can see, if you look here at the task signal here, and here in whatever this is red, we have here the highest performance. You see it really corresponds here 5 with 5, 25 with 25, 4 with 4, 9 with 9, and 2. So this is what the authors, what UC Berkeley found. And I think this is interesting. But don't you dare to think that this might be the same for all large language models. This is just for one very particular Llama 3, not a Llama 4 by the way, Llama 3 model. And it depends heavily on the pre-training data cycles. If the pre-training would have encoded a different, I don't know how to say this, thinking process of the large language model, the in-context learning calculation might have been performed in a complete different subspace with a complete different periodic pattern. So this is just for one example how it works. We cannot generalize this. Let's come here to an end. So I think it's fascinating that we finally understand that the LLM doesn't just learn one way to see here a unit digit. It'll learn here a multifaceted view by decomposing K according here to several periodic functions. And this kind of periodic view that the LLM develops, K modulo 2, K modulo 5, K modulo 10, are discovered here by using here in the simplest case a PC and then rotating here the direction that have pure trigonometric functions. We have a unit subspace of 4-dimensional and then another 2-dimensional amplitude space. And you see this distributed periodic encoding as absolutely a surprisingly sophisticated strategy for this seemingly simple task just to add an integer, just to add a number to another number. This is how an LLM does it. No, this is how this very specific LLM does it. If another LLM has been subject to other pre-training, training data, or has a different layer architecture, has a different dimension in its attention head, has a different connectivity between its layers, have different normalization function, or might have different non-linear transformation for the learning process itself, we might encounter a complete different learning process. And this is just in context learning, and I think it's absolutely fascinating. So don't stick to this particular code, but just understand that this code is just one of a multitude of code morphisms. I did not, in preparing this video, started with the quantum example. I started here with an organic cell, and I thought, hey, it would be great if I could show you how to build an organic cell that can perform an in-context learning, a Llama 3 operation in a wet environment, in an organic environment. Think about this. This is the same. We have now not a neural network encoding. We have not a matrix multiplication representation for the encoding of knowledge and function and operation. But here we deal now with a complete different form of intelligence. Let's call it a wet intelligence. And you know what? You won't find this solution if you just look for the code for your Python compiler. You need to look for the code for your brain. And you know, I see that so many people, you know, they say, hey, the limits of my computer hardware, of my GPU, VRAM, or whatever, this is what I can code. This is the limit of my thinking. And I think this is so sad, because what NVIDIA graphic card you have available for your AI runs is not limiting your intelligence, your creativity, and your thinking to understand that intelligence is not simply one form and one code. Maybe in each different LLM, we have a different way how the intelligence is implemented, even for the simplest task of adding an integer. And I want to give you this example. If you try to find here the solution here in the wet environment for coding intelligent systems, I want just to give you a hint for your solution. I thought about ATP synthase as a molecular machine. You remember, in our cells, we have, nature created over thousands and millions of years a metabolism where at the cell membrane we have a three-dimensional molecular machine. The function is to pump protons out into another region. So we have a complex three-dimensional molecular machine, extreme complex, rotating, performing here translation operation just for one goal, to transfer single protons out of the cell. If you think about this, and yeah, if you know adenosine triphosphate, adenosine diphosphate, and inorganic phosphate, this is such a beautiful machine, an artificial intelligence, that you see you're not working here with different layers of a transform architecture, but here in the wet environment, you have to encode the intelligence with three-dimensional molecular compounds. So again, from the paper UC Berkeley, you see this. For our classical Llama 3, they're finding the projection head activation space is now reduced from a 128-dimensional to the 6-dimensional to preserve here the necessary task information for the simplest task of having just add K operation. And then this space here has another specialization. So it factors into a 4-dimensional space capturing the unit digit and a 2-dimensional space capturing the 10 digits. But this is just one of the form you can code this. And this is only valid for a complex matrix multiplication schema we call a transformer architecture with a self-attention mechanism. But you know what? You will not transcribe this, you cannot map this in a wet biological system. You have there not your matrix multiplication, but you have there different elements, different tools you have to use. You have to use molecular compound. You have to understand the three-dimensional dynamic of a molecular compound in a wet system. And I can tell you the operations there are not to be decomposed in periodic functions. So if you would like to take this exercise for you, if you would like to think about how to code a wet intelligence in a biological system, you achieved what hardly anybody else achieved before you. You are not looking just for code for your Python compiler, but you're really trying to understand how we can code intelligence in a quantum morphism or in a wet biological system. And I think this is the beauty of AI. It is about intelligence. If you like to subscribe, I see you in my next video.